So in question number 39, under option A, it is given that all, we need to identify the incorrect statement. Okay, option A is all the 5D orbitals are different in size when compared to the respective 4D orbitals. Okay, see, size of the orbitals. Okay, very specifically, if you take d orbitals, okay, alone d orbitals alone, if you compare the size of 3D and 4D, okay, size of 4D orbitals are larger. And if you compare 4D and 5D, yes, size of 5D orbitals are larger. Okay, as this number is n, actually n quantum number, principal quantum number. As principal quantum number increases among same type of orbitals, then size will increase. Okay, if the orbitals are same, 3D, 4D, 5D, then as the principal quantum number increases, size increases. Okay, so read the option A again. All the 5D orbitals are different in size. Yes. Okay, 5D orbital size are different when compared to the respective 4D orbitals. Yes, definitely the size are different. So option A, the statement is a correct statement. Then option B, in option B, all the 5 4D orbitals have shapes similar to the respective 5D orbitals. Observe this carefully. If you compare 3D and 4D, okay, in 3D we have 5 orbitals. What are they? 3D xy, 3D yz, 3D xz or xz, then 3D x square minus y square orbital, then 3D z square orbital. Similarly, in 4D we have 5 orbitals. Okay, 4dxy, 4dyz, 4dxz, then 4dx square minus y square, and 4d z square. Okay, in 3D we have 5D orbitals. In 4D we have 5D orbitals. If you compare their size, definitely size of 4D orbitals are larger, no doubt. But what about the shape? Shapes are same actually. Okay, shape of dxy, 3dxy, 4dxy, 3dyz, 4dyz, 3dxz, 4dxz. Shapes are same actually. Okay, you know very well the shape of dxy orbital. Let me draw here. I'll fix the axis like this, x and y. Okay, or x and this is y. Let me take this is y and this is z axis. Okay, dxy orbital. Dxy orbitals have lobes in between x axis and y axis. So in between x, okay, and y. D orbital have dxy orbital has 4 lobes, and the lobes are present in between x and y axis. So this is the shape of dxy orbital, dxy. Right? Then dyz have the lobes. I'll fix the axis as such. I'm not going to change the axis. Okay, fix the axis as such. Now we need to draw yz orbital, which has 4 lobes. The lobes are present in between y and z. So this is y axis, this is z axis. So in between y and z you have to draw. Okay, like that you have to draw. So this is the shape of dyz orbital. Right? Then dxz. What is the shape of dxz orbital? Let me draw here. This is x axis, this is z axis. Okay, this is y. Now for dxz orbital, the lobes should be in between x and z. So this is x axis, this is z axis, x axis, z axis, x axis, and z axis, here x and z. So this is the shape of dxz orbital. Then dx square minus y square, dx square minus y square have lobes along the axis. See, these d orbital have lobes, okay, in between the axis, whereas dx square minus y square that I am going to draw now, dx square minus y square, they have lobes along the axis. So this is x-axis, y-axis, z-axis. They have lobes along x-axis and y-axis. So you have a lobe along plus x and minus x, and you have another lobe along plus y and minus y. Okay. Then last one, dz square orbital, I'll draw here. dz square orbital. So here we have x. This is the y-axis and this is z-axis. Now dz square orbital have lobes along the z-axis. Along the z-axis, and there is a circular collar in the xy plane. There is a circular collar in the xy plane. Okay, these are the shapes of the d orbitals. Okay, observe this carefully. Whether it is 3dxy, 3dyz, or 4dxy, 4dyz, 4dx square, whatever maybe it is, between these only size is different. Okay, 4d orbitals have larger size, that's all, but shape remains the same. Okay, remember these three orbitals have lobes in between the axis, and this orbital have lobes along the axis. This orbital also has lobe along the axis. These four orbitals, okay, they have four lobes. Okay, they have four lobes, right? And their shapes are similar to double dumbbell, whereas this orbital shape is different. D is a square orbital shape is different. Okay, take note. So for question number 39, if you see the option B, all the 5 4d orbitals have shapes similar to the respective 3d. Yes, that is correct. This is also correct statement. This is also correct statement. Okay, statement A is correct, statement B also correct. What about statement C? In an atom, all the 5 3d orbitals are equal in energy in free state. Yes, that's correct. In free state, okay, just note on this one. I'll go to the next page. So in d orbitals, remember these are the shapes of the 5 d orbitals. Okay, dxy, dyz, dxz, and these three orbitals have lobes in between the axis. Dx square minus y square have lobes along the axis, and dz square also have lobes along the axis, and here we have a circular collar in the xy plane. Okay, dumbbell with the donut, right? That's what we say. So this circle appear like a donut. So we say that it is a dumbbell with a donut. These four are double dumbbell structures, shapes. Now let me go to option C. In option C, in an atom, all the 5 3d orbitals are equal energy in free state. Observe this carefully. This is very important. In free state means the atom or the ion, okay, the atom or ion are not involved in any of the external influence. Okay, it is not it's not in the, it is in the free environment. That's the meaning. Okay, so in free state, right, in free state, remember, suppose if we take a p subshell has 3 orbital. Okay, all the 3 orbitals have equal in energy in free state. Okay, in free state, all the d orbitals, okay, dxy, dyz, dxz, dx square minus y square, and dz square. All the 5 orbitals have same energy. Okay, in free state, remember, all the in a subshell, all the orbitals have same energy. Okay, so that's the point you should keep in mind. Right, take down. So option C also a correct statement here. What about option D? In option D, it was given the shapes of dxy, dyz, and dzx orbitals similar to each other, and dx square, y square, dz square are similar to each other. That statement is wrong. Why? See, the dx square, y square and dz square are the two have same shape? Dx square, y square and dz square are the two have same shape? No. This is double dumbbell shape, right? Double dumbbell shape where lobes are along the axis. Whereas this one is a dumbbell with a donut at the center, right? Okay, these two orbitals, okay, they do not have the same shape. Okay, see option D. In option D, shapes of dxy, dyz, dxz orbitals are similar. Correct. That is correct. All the 3 d orbitals have double dumbbell shape. Whereas one more statement is given in the same option, and dx square, y square and dz square are similar to each other. No. The shapes of these two are different. Therefore, the incorrect statement for question number 39 is option D. Note down. So for question number 39, the correct option is D. Is this clear?
Yes, sir.
Yeah. Let me go to the next question. Question number 40. 4D, 5P, 5F and 6P orbitals are arranged in the order of decreasing energy. The correct option is, okay, this is a very important question, often expected in the examination. Okay, 5 orbitals are given, 4D, then 5P, then 5F, then 6P, right? 4 orbitals are given. Observe this carefully. This number is nothing but principal quantum number. Okay, so for 4D, principal quantum number is 4. For 5P, principal quantum number is 5. For 5F, principal quantum number is 5. Okay. Similarly, for 6P, principal quantum number is 6. So this number, front number, indicate the principal quantum number. And you know very well, the azimuthal quantum number L for different orbitals, okay, say for s orbital, azimuthal quantum number is 0. For p orbital, azimuthal quantum number is 1. For d orbitals, azimuthal quantum number is 2. Okay, then for f it is 3. Remember this. For s, L equal to 0. For p, L equal to 1. For d, L equal to 2. For f, L equal to 3. Okay, now to arrange these orbitals in the increasing order of energy, you need to see n plus L values. N plus L value you have to see. Okay, so here, listen here, what is the value of n plus L? Let me write. N value is 4. For d orbital, L value is 2. So 4 plus 2, it is 6. Okay, then for 5p, n value is 5. For p subshell, L value is 1. So 5 plus 1, that is also 6. Then for 5f, n value is 5. For f subshell, L value, for f orbital, L equal to 3. So 5 plus 3, 8. Then for 6p, n value is 6. For p, L value is 1. So 6 plus 1, 7. Okay. Observe this carefully. If n plus L is high, energy that orbital has higher energy, or that subshell has higher energy. Okay, so subshell or orbital having higher n plus L value. Subshell or orbital having higher n plus L value has higher energy. Very simple. So tell me, among these which one is highest? 6, 8, 7. Which one is highest value? 8. 8 corresponds to which orbital? 5f orbital. And read the question again. 4d, 5p, 4f, 5f, 6p orbitals are arranged in the order of decreasing energy they are asking. You have to arrange in decreasing energy, right? So among the one which is highest energy, if n plus L is high, this is n plus L value. If n plus L is high, that orbital has highest energy. So among the 4, the highest energy orbital is 5f. 5f. Then so we have selected this. Then among these 3, the next higher energy is 6p. N plus L value is 7. Okay, among the 3, right? These 3. The next higher value is this. We finished off. Then for these 2, see, n plus L values are same. Whenever n plus L value is same, if n plus L value is same for 2 orbitals or 2 subshells, if n plus n values are same, let me write like that. If n plus L values are same for 2 orbitals, then orbital having higher n value has higher energy. That's the point. Okay, so these 2 orbitals, they have same n plus L value. Now you should see the n value actually. So which one has higher n value? 5p has higher n value. Therefore 5p has higher energy. 5p. Then the last one is 4d. So this is the arrangement. This is how we arrange the orbitals in the decreasing order of energy. Okay. So which option is correct? Just go through that. 5f, then 6p, then 5p, then 4d. So the correct option is B. Option B. Clear? Okay. Yeah.
Yes, sir.
Remember this information. This is very important. First of all, you should see n plus L value. Higher the value, higher is the energy. If 2 orbitals have same n plus L, then you should see the value of n. Okay, higher the value of n, higher is the energy. Take down. Finished?
1 minute, sir. Okay, sir.
Right. Then see question number 41. Here they are asking orbital having 3 angular nodes and 3 total nodes. Okay, orbital having 3 angular node and 3 total node. Okay, see here. First of all, I'll give this information or formula, right? Number of, right, in orbitals, students observe carefully. Orbitals have two different types of nodes. Okay, there are two different types of nodes. Number one, radial node, then the second one is angular node. Orbitals have two types of nodes, radial node and angular node. Okay, number of radial nodes, how many radial nodes present in an orbital? Number of radial nodes, this is the formula, n minus L minus 1. N is principal quantum number, L is azimuthal quantum number. Okay, then number of angular nodes, equal to just the value of L. Total number of nodes, nodes equal to, you have to add these two. If you add, you will get n minus 1. Okay, remember this is very, very important. Now, using this information, I am going to answer question number 41. Read the question again. Question number 41, orbital having 3 angular node. 3 angular node means L value is 3, correct? Because number of angular node is nothing but L. So, it is given 3 angular node, so L value should be 3. L value 3 means which orbital it corresponds to? It corresponds to F. F subshell or F orbital. L equal to 0 means, okay, in the last page I have told you, L equal to 0 means S subshell, 1 S orbital, L equal to 1 means P, L equal to 2 means D, L equal to 3 means F. So here angular node is given 3. Angular node is nothing but the value of L. Okay, therefore L value is 3. If L is 3, the orbital, the corresponding orbital is F. Okay, then, and 3 total nodes are there. Total number of node equal to n minus 1. So n minus 1, it is given 3 total node. Okay, so n minus 1 equal to 3 or n is equal to 4. Bring this minus 1 this side, 3 plus 1, 4. Therefore, that orbital or the subshell should be 4f. N value 4 and subshell is f, therefore the orbital is 4f. So correct option. Which is the correct option?
C.
C, yeah, take it. It's very simple, okay? Then, so remember this is very important, right? So number of radial node, number of angular node, then total number of nodes. Okay, then see the next question, question number 42. Did you copy this?
1 minute, sir. Okay, sir.
Yeah. On to the next question. Question number 42. Just go through the question. Which one is wrong statement? They are asking wrong statement. Question number 42. Yes. Option A. Total orbital angular momentum of electron in s orbital is equal to 0. Students, observe carefully. Total angular momentum. What is the formula? Total orbital angular momentum. Okay, this is very important. Total orbital angular momentum, okay, is given by the formula square root of L into L plus 1 into h by 2 pi. This is the formula for total orbital angular momentum. Okay, now in option A, it is given that total orbital angular momentum of electron in s orbital is equal to 0. Yes, total orbital angular momentum of electron in s orbital. For s orbital, L value is 0. Remember, for s orbital, L value is 0. Therefore, if I put L equal to 0 here, 0 into whatever it is 0, square root of 0 is also 0, 0 into this 0, so the entire value becomes 0. I repeat, if L is 0, this becomes 0. If this is 0, this is all into this, so that is also 0. So total orbital angular momentum of electron in s orbital is 0. Yes, that is a correct statement. Okay, statement A is a correct statement, correct? What is given? See, total orbital angular momentum of electron in s orbital equal to 0. That's correct statement. Okay, then what about B? Is this clear? Here, remember this formula. This is very important. This is the formula we use to calculate total orbital angular momentum of electron. Okay, then see the next option. An orbital is designated by 3 quantum numbers, while an electron in an atom is designated by 4 quantum numbers. Yes, that statement is correct. Option B, listen, we represent orbital, okay, we designate orbitals with the 3 quantum numbers n, L and m. Whereas electrons in orbital we represent with the 4 quantum numbers L, m, n, L, m and spin quantum number s. Yes, this is correct. Okay, I repeat. In option B, see, an orbital is designated by 3 quantum numbers. Yes, orbital is designated by 3 quantum numbers. Whereas while an electron in an atom is designated by 4 quantum numbers. Yes, that's correct. That's correct. Take down. It's a correct statement. And remember this information, very important. We designate orbitals with the 3 quantum numbers. We designate electrons in atom or electrons in orbital with the 4 quantum numbers. Okay. Then see option C. In option C, the electronic configuration of nitrogen atom is given. Nitrogen atomic number 7. So there should be 7 electron. 1s2, 2s2, 2px1, 2py1, and 2pz1. See, the arrow mark is given in the downward direction. Okay, that means this, see, 2py have plus of, 2pz electron has minus of spin. So they cancel, right? Okay, only 2px spin remains. So the spin multiplicity value is less. Observe this carefully. Observe this carefully. So in nitrogen atomic number 7, right, 1s orbital has 2 electron, 2s orbital has 2 electron. In 2p subshell, 3 orbitals are there. Okay, 3 orbital. What are they? 2px, 2py and 2pz, and in that the electronic configuration is given like this. 2 electrons have upward in the upward direction, the other one is downward direction. What is the meaning? These 2 electrons have same spin. This electron is opposite spin. So what is the spin multiplicity? We have to calculate spin multiplicity. Let me calculate here. Spin multiplicity. Okay, what is the formula? The formula is this: 2s plus 1. 2s plus 1. Okay, this is the formula for spin multiplicity. Here this capital S, okay, is nothing but sum of the spins of each electron. So if the electron has upward spin, put plus half. Then second electron also have upward spin, plus half. Whereas the third electron has downward spin, put minus half. So plus half minus half cancel, so total spin also plus half. If we put plus half here, 2 into 1 by 2 plus 1, I will get the spin multiplicity as 2. Suppose in the same, if in nitrogen atom, students observe carefully, 1s 2 electron, 2s orbital has 2 electron. In 2p, Suppose if all the 3 electrons have same spin, upward spin, suppose if the electronic configuration exists like this, then what will be the multiplicity? 2s plus 1 equal to 2 into, now what's the value of s? This is plus of, this is plus of, this is also plus of now. So if you add all the 3, you'll get 3 by 2. So spin value becomes 3 by 2 plus 1, 2 cancel, I'll get 4. Okay. So if electrons have same spin in a subshell, okay, this is a subshell. In a given subshell, if the electrons have same spin, spin multiplicity will be high. See here, 2 electrons have same spin, another electron is given in the opposite spin, therefore spin multiplicity is less. Configuration having high spin multiplicity, okay, is highly stable. Okay, whereas this configuration is not that stable, therefore this is not the configuration of nitrogen. Okay, for nitrogen this is the correct configuration. Why? Because they have high spin multiplicity. Okay, take down. If two electronic configuration, suppose if they give electronic configuration, whether it is correct or not, what you have to do, you should see the spin multiplicity. If the spin multiplicity is high, that is the highest possible for the given configuration, that configuration is a stable configuration, you can say. But for this, we have another possible configuration. This configuration has high multiplicity compared to that. So this is the correct configuration, not this one. So for option C, in option C, electronic configuration nitrogen atom is given with the 2 electron in p subshell. 2 electrons have upward spin, 1 electron downward spin, so spin multiplicity is low, therefore this cannot be the correct configuration for nitrogen atom. It is not a stable configuration. Okay, so this configuration, okay, has more stability due to exchange energy. Yeah, then so option C is the wrong statement here. Therefore, the correct option for this question is C, because we need to identify the wrong statement. So wrong statement is C. And what about option D? See option D, the value of m for dz square is 0. Students, observe carefully, this is very, very important. Option D. Listen. Among p orbitals px, py and pz, pz orbital have m value 0. Remember, always whenever orbital has only z, pure z, m value should be 0. Similarly in d orbital, dxy, dyz, dxz, dx square minus y square and dz square. See, here we have x with y, we have y and z, x and mixed, these are all mixed. Here also x and y mixed, whereas this is dz square has only z, correct? Only z. Whenever orbital has only z, then m value should be 0. This is another important point you should keep in mind. So among p orbital, pz orbital has m value 0. Among d orbital, dz square orbital has m value 0. Okay. Option D is a correct statement, but you need to remember this information. If m value is 0, this is the point. If m equal to 0, then the orbital should contain only z. Okay. Orbital symbol contains only z. Okay, either pz or dz square or dz cube, like that. Okay, if you go to f subshell, you will get dz cube or fz cube. I'm sorry, fz cube. So that's for that m equal to 0. Remember this. So for question number 42, the correct option is C, because that option is a wrong statement. Clear?
Yes, sir.
Yeah, let me go to the next question. See this one, question number 43. Which one is the wrong statement? You need to identify the wrong statement. Option A, the uncertainty principle is delta E into delta T is greater than or equal to h by 4 pi. Yes, that is the correct statement. 43. Option A. You need to identify correct statement. Student, remember uncertainty principle. Uncertainty principle. We normally write Heisenberg uncertainty principle, which is the uncertainty in position and uncertainty in momentum. If you multiply these two, delta x into delta p is greater than or equal to h by 4 pi. Okay, this is Heisenberg uncertainty principle. Apart from this, we have other uncertainty principles. Okay, the other one is given here, delta E into delta T. Uncertainty in energy and uncertainty in time measurement. Okay, if you multiply these two, this value is also greater than or equal to h by 4 pi. This is also uncertainty principle. Student, this is also uncertainty principle, note down. We have one more uncertainty principle in terms of angular momentum, but that is not required for us. So in option A, this uncertainty principle is given. So option A is a correct statement. What about option B? Off-filled and fully filled orbitals have greater stability due to greater exchange energy, greater symmetry and more balanced arrangement. Yes, that's correct. If you have all filled, off-filled or fully filled orbitals, suppose I'll take p subshell. I'll take a p subshell. In p subshell, we have 3 orbitals. If all the orbitals have 1 electron off-filled, yes, it is stable. If all the orbitals have fully filled electron 2, 2, 2, this is also stable. These two arrangements are stable. Why they are stable? Because if the electrons have same spin, then they can exchange. They can exchange. So this electron can exchange with that, and these two can exchange. Okay, so remember, you can exchange 2 electrons if they have same spin. Therefore, due to more exchanges, okay, possible here, this arrangement, off-filled arrangement, is more stable. Similarly here, we have 3 upward electron and 3 downward electrons, so we have more exchanges possible. Okay, due to exchange energy, right, these two are stable. Off-filled and fully filled subshells are stable. Not only p subshell, even if you go to d subshell, off-filled, fully filled are stable. It is because of exchange energy. So due to greater exchange energy and greater symmetry and more balanced arrangement. Yes. Option B, that statement is a correct statement. Okay, then let me go to the next one. Remember this, off-filled, fully filled structures are stable. Okay. Then option C, just go through that. The energy of 2s orbital is less than the energy of 2p orbital in case of hydrogen-like atoms. The energy of 2s orbital is less than the energy of 2p orbital in case of hydrogen-like atom. See, this is very important. In the case of hydrogen-like atom, hydrogen-like means it consists of 1 electron. We have only 1 electron, so there is no electron repulsion, correct? We have only 1 electron. Okay, suppose if you have 2 electron, then there may be electron repulsion. Since hydrogen-like atom has only 1 electron, there is no electron repulsion. Therefore 1s orbital has lowest energy. Then 2s, 2p subshells, okay, or 2s orbital. In 2p we have 3 orbital, 2px, 2py, 2pz. All these orbitals have same energy. 2s and 2p orbitals all have same energy in the case of hydrogen-like atom. Similarly, if you go to 3s orbital, then 3px, 3py, 3pz, then 3d orbital, we have 5 here, 3dxy, 3dyz, 3dxz, 3dx square minus y square, and 3dz square. Right, all these orbitals have same energy. In the case of hydrogen like atom, because we have only one electron, there is no electron repulsion possible. Okay, therefore see the option C again. Energy of 2s orbital is less than energy of 2p is given. See this, see the statement, read the statement carefully. It is given less. No, all the orbitals have same energy actually in the case of hydrogen like atom. So the statement C is a wrong statement. Okay, but it is the correct option for our question, because we need to identify the correct option. Okay, take 2. If you go to other atoms where you may have more than 2 electron, or you may have more than 1 electron, whenever atom contains more than 1 electron, then electron repulsion will come. Okay, when electron repulsion comes, then 2s orbitals, 2px, 2py orbital, they cannot have same energy. Okay, the energies of the orbital will differ. Is this clear?
Yes, sir.
Yeah. Then see option D. Yes, anyway, option C is the wrong statement, we have found out. Just go through option D also. See, de Broglie's wavelength is given by lambda is equal to h by mv, where m is the mass of the particle, v is the group velocity of the particle. Yes, that's correct. That's correct. Lambda is equal to h by mv, right? That is the equation called de Broglie equation, right? This is a correct statement. So the only wrong statement is option C, right? Take down. Then see question number 44. Question number 44. Question number 44. Read the question carefully. How many electrons can fit in the orbital for which n equal to 3, l equal to 1? Observe this carefully. N equal to 3 and L equal to 1 is given. So what subshell is this? First I'll find out the subshell. What subshell? If n value, L values are available, you can find out the subshell. So n value is 3, L value 1 means the subshell is P subshell, you know that. Okay, L0 means S, L1 means P subshell. In P subshell, 3P subshell, we have orbitals. How many orbitals are there? There are 3 orbitals. 3p subshell has 3 orbitals. What are they? 3px, 3py, and 3pz. So for all the 3 orbitals, okay, n value is 3, l value is 1. Okay, read the question again. Carefully you have to read. How many electrons can fit in the orbital? They are asking orbital. They are not asking subshell. In the subshell, you can place maximum of 6 electrons. Whereas in orbital, in each orbital, you can place only 2 electrons. Maximum 2 electrons. So that this 2 plus 2 plus 2 will get 6 totally. But in each orbital, you can place only 2. You can place only 2. So how many electrons can fit in the orbital for which n equal to 3, l equal to 1? The correct option is A. Because in each orbital, you can place only 2 electrons. And here, remember this formula. This is a very useful one. Maximum number of electrons, right, in a main shell, K shell, L shell, M shell, like that, in a main shell, okay, is equal to, this is the formula, 2n square, where K shell For K shell, n value is 1. For L shell, n value is 2. For M shell, n value is 3. For N shell, n value is 4, like that. Then maximum number of electrons in a subshell. In a subshell, what is the formula? The formula is 2 into 2L plus 1. Stuck once again. Yeah, 2 into 2L plus 1. You can also write like this: 2 into 2, 4. So 4L plus 2. This is the formula that will give you maximum number of electron possible in a subshell. Okay, so here see, here the subshell given is 3p, p subshell. For p subshell, L value is 1, right? For p subshell, L value is 1. You put L value 1 here. If you put L value 1, 4 into 1, 4. 4 plus 2, 6. Yes, you have 6 electron maximum. You can place maximum 6 electrons. Then maximum number of electrons in an orbital. Is just 2. Maximum you can place only 2 electrons in an orbital. Okay, remember this is very important. Maximum number of electrons in a main shell, maximum number of electrons in a subshell, maximum number of electrons in an orbital. So whatever may be the orbital, whether it is d orbital, p orbital, s orbital, you can place maximum of 2 electron in that. Each orbital can accommodate only 2 electron. Okay. Yes. Is this clear?
Yes, sir. Yes, sir.
Yeah. Just note down.
Yes, sir.
Okay, ma. Now let me go to the next question. See question number. Did you copy this?
Yes, sir.
Okay, ma. See question number 4. Okay. For question number 44, what is the correct answer? Correct answer is option A, right? Option A. Now let me go to the question number 45. Which of the following pairs of d orbitals will have electron density along the axis? Along the axis. I have told you about this already. Which orbitals have lobes along the axis? You tell me. Which are all the orbitals have lobes along the axis? We have discussed this already. See, just for your reference, I'll keep this one. Which are the orbitals have lobes along the axis? These 3 orbitals have lobes in between the axis, correct?
Yes, sir.
Whereas only these 2 orbitals have lobes along the axis. Yeah, so dx square y square and dz square orbitals have lobes along the axis. Okay, take it. So for question number 45, tell me what's the correct answer. Which 2 pairs of orbital have axis along the same axis and density along the axis? Identify the option.
D, sir.
No, it's option C, no? Option C, right?
C. Okay, sir.
In option C, we have these 2 orbitals, dx square y square and dz square. These 2 orbitals have lobes along the axis, correct? These 2 orbitals have lobes along the axis, so correct option is C. Okay, let me go to the next question. Yeah. See, question number 46. 2 electrons occupying the same orbital are distinguished by 2 electrons occupying the same orbital. If 2 electrons occupy the same orbital, you know very well, question number 46, you know very well, if 2 orbital have same, if 2 electron occupy same orbitals, okay, suppose I'll take an orbital, right, and we have 2 electrons here, 2 electrons. Okay, I'm going to place 2 electron 1, electron 2. Okay, for an orbital, n value, l value, m value are always fixed for an orbital. Okay, but for electron, for each electron, there are 4 quantum numbers. Okay, they have same, since the 2 electron present in the same orbital, they have same n value, they have same l value, and they have same m value. These 3 remain same. But the 4th quantum number spin, that differs. Actually, one electron have plus half spin, another electron have minus half spin. I repeat, for an orbital, okay, 3 quantum numbers are required. So if you take a particular orbital, for that orbital, n value, l value, m value are fixed. So if you have 2 electrons in that, right, both the 2 electrons have same n, l, m values, same n, l, m values. Then which one will differ? Only the spin quantum number differ, because electrons have 4 quantum numbers. Electrons have 4 quantum numbers, so spin quantum number must be different. Otherwise, Pauli principle does not obey. Okay, so S is equal to plus half for one electron, then S is equal to minus half for other electron. Is this clear? So, can you tell me the answer? Can you identify the answer? 2 electrons occupying the same orbital are distinguished by azimuthal quantum number, spin quantum number, principal quantum number, magnetic. Which one is correct?
Spin.
Spin quantum number, option B. Yes. Only the spin value differ. Question number, let me go to the next question. Did you copy this?
Yes, sir.
Yeah. See, question number 47. Which is the correct order of increasing energy of the listed orbitals in the atom of titanium? In the atom of titanium. Okay, which is the, and atomic number is given. Atomic number is 22. Which is the correct order of increasing energy? You have to identify. But remember, suppose if you know the electronic configuration order, you just write, okay, directly. Suppose if you forget, okay, then you just remember this Abba principle. Okay, what does that say? We have 1s subshell, then in the second subshell we have 2s and 2p. In the first main shell we have only one subshell. In the second main shell we have 2 subshell. In the third main shell we have 3 subshells, 3s, 3p, 3d. And in the fourth main shell we have 4 subshells, 4s, 4p, 4d and 4f. Then 5s, 5p, 5d, 5f. Okay, these are the subshells present in fifth main shell. Similarly, we have 6s, 6p, 6d, 6f. Okay, remember this arrangement. Now, according to Abba principle, you have to go the energy increasing in this order. First, the lowest energy is 1s. Then go in the middle. The next energy, next higher energy orbital is, or a higher energy subshell is 2s. Then after 2s, you should go to 2p. You fill 2p, then fill up 3s. Then go in the middle. Then fill up 3p and 4s. Then go in the middle and put a line here. Okay, so in this way you have to arrange the electrons. This will give you the increasing order of energy of the orbital. Okay, so listen, in the given question it is given titanium. Titanium symbol is Ti and atomic number is given, which is 22. So that means there are 22 electrons available. Now we have to fill up the electron in these subshells. Okay, let me write. The first subshell is 1s. In 1s you can place maximum of 2 electrons. The second subshell is 2s. Yes, in S subshell, whether it is 1s, 2s, 3s, in F subshell, S subshell, you can place maximum of 2 electrons. Then after 2s, you have to go to 2p. In 2p, in p subshell, you can place maximum of 6 electrons. Then after filling 2p, we have 3s. In 3s, S subshell, we can place maximum of 2 electrons. Okay. Then after 3s, we have 3p. In 3p you can place maximum of 6 electrons. Let me count the electron because we should not go beyond 22, right? So 2 plus 2 4, 4 plus 6 10, 10 plus 2 12, 12 plus 6 18 electron we filled up, remaining 4. Okay, so after 3p we have to fill up 4s. So 4s 2 electron. Then after 4s we have 3d. Yes, in 3d we have to put 2 electron. 4s2, 3d2. Okay, therefore the correct arrangement is this. Students, observe this carefully. So this is given actually. These 4 orbitals are given, right? In all the option, 4 subshells are given. Okay, so we have 4 3. You have to take the arrangement starts from 3s. Okay, so which arrangement starts from 3s? Option A definitely wrong because it starts from 4s. In option B it starts from 3s. The next one is 3p, correct? Then 3d 4s. And see student, here this is very important. Yeah, this arrangement is correct. Okay, this arrangement is correct, no doubt in that. Okay, so you can say that for this question the correct option, let me give the option here. Listen, students, this is the arrangement. So which is the correct option? Tell me. Which option has this arrangement? 3s, 3p, 4s, 3d.
C.
Option C. That's all. So if you forget how to write the electronic configuration, just remember to write this. Okay, you just write this, and from this you can easily fill up electron. Remember, these are all subshells. And in S subshell, you can place maximum of 2 electron. In P subshell you can place maximum of 6 electron. In D we can place maximum of 10. In F subshell we can place maximum of 14 electrons. Okay, remember this. Is this clear?
Yes, sir.
Yeah. Then let me go to the next question. Question number 48. The number of d electrons in Fe2 plus. Question number 48. Number of d electrons. They are asking, yeah, number of d electron, right? Number of d electron. Read the question carefully. Number of d electrons in Fe2 plus. For Fe atomic number is 26. Is not equal to the number of electron in which one of the following? Okay. Listen. For iron, atomic number is 26. So what is the electronic configuration? Let me write the electronic configuration. Okay. Let me write the electronic configuration first. We should start from 1s, right? 1s, then 2s. Okay. So let me write it. 1s2, 2s2, 2p6, then 3s2, 3p6. So up to this 18 electrons over. Then we have 3d4s. Okay. For iron, actually, listen student, while writing we'll write like this, but whenever D and S subshells are present as outer shell, when D and S are present as the valence, then place 2 electron in S first, then place the remaining electron. The remaining electron is 6. Okay, because the total number should be 26, correct? So here we have 18 plus 2, 20, 26. Always remember, if D and S are present as outer shell, okay, then fill S subshell first, then place the remaining electron in D. This is the procedure. Okay, this is we are doing just for the purpose of stability. Right now, when you remove 2 electron, you'll get 2 plus Fe2 plus ion. So for Fe2 plus ion, we are going to remove 2 electron from the s orbital. If I remove 2 electron, then 3d subshell, keep all other things as such. Keep all other things as such. 3d subshell contains 6 electron. Okay, so it is given that in ion 2 plus, d subshell has 6 electron. It is given, that statement is given. The number of d electron in Fe2 plus is not, number of d electron in Fe2 plus is 6, okay. So in Fe2 plus, number of d electron, okay, because we have other orbitals are just s and p, only this d is there, so number of d electrons is 6 actually in Fe2 plus. In Fe2 plus, number of d electron is 6. Now we need to identify in the given option which one is not equal to the number of electron, that is not equal to 6, we have to identify. Okay, d electron in Fe, students observe carefully, this is d electron in Fe2 plus. Fe2 plus has 6 electron. Even if you take Fe, Fe also have only one d orbital, d subshell, which has 6 electron. So in option A, d electron in Fe is given, okay, that is 6, correct. Listen, Fe2 plus has d electron 6, ion also has d electron 6, okay, but we need to identify which one is not equal to 6, okay. Then option B, p electron in neon, p electrons in neon configuration is this: neon 1s2, 2s2, 2p6, neon atomic number 10, so the configuration is 1s2, 2s2, 2p6. Then p subshell has 6 electron, yes, same, like ion 2 plus, like 6 electron in D, in Fe2 plus, we have 6 electron in p subshell of neon, that is correct, equal. Then option C, s electron in magnesium, students observe carefully, s electron in s orbital, okay, let me write magnesium. What is the electronic configuration of magnesium? Magnesium atomic number is 12, so 1s2, 2s2, 2p6, we have filled up 10 electrons, then 3s2, okay. Now listen, how many s orbitals are there? S subshells, we have 3 s subshells, so total number of s electrons is 6, correct. 2 plus 2 plus 2, this is also 6. Then let me go to option D. Right, in option D, p electrons in chlorine they are asking. Chlorine atomic number 17, the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p5. You just check it afterwards. There are totally 17 electrons. Now you have to count p. Okay, here you have a p, here you have a p. So this is 2p, this is 3p. Okay, so total is 6 plus 5, 11 electrons. 6 plus 5, 11 electrons. Okay, so p electrons in chlorine, right, is 11, not 6. In all the three options, see, the given statement matches with the 6 electron. The given option matches with 6, but in option D, it is given that p electrons, but there are 11 p electrons, which is not matching. So the correct option for this question is option D. Take 2. They are simply asking p electron. They are not specifying whether it is 2p or 3p. Correct. So in this case, you have to count all the p electrons. All the p electrons. Similarly here, all the s electrons. Right. Is this clear? Any doubt?
No, sir. No, sir.
Yeah. Yes, ma'am. Take 2. Let me go to the next question.
Yes, sir.
Question number 49. The angular momentum of electron in d orbital is equal to d orbital. D orbital, you know very well, for d orbital L value is 2. To find orbital angular momentum, you require L value. So what is the angular momentum of electron? Right? Angular momentum, orbital angular momentum, because it is given orbital. Orbital angular momentum, total angular momentum, right? Total orbital angular momentum. Total orbital angular momentum is equal to, this is the formula, square root of L into L plus 1 into h by 2 pi. This h by 2 pi should be separate. You have to write separately. We should not write inside the square bracket. Then put L equal to 2 here. 2 plus 1. Keep this one as such. Right? This is equal to, I'll keep this 2 as such. 2 plus 1 is 3. So 2 into 3 is 6. So root 6 into h by 2 pi. Root 6 into h by 2 pi, that is the orbital angular momentum of the electron. And remember, h by 2 pi can also be written as h cross. Remember, h cross is nothing but h by 2 pi, student. Observe carefully. H cross is nothing but h by 2 pi. So you can also write like this. Total orbital angular momentum equal to square root of 6 into h cross. Clear? Any doubt?
Yes, sir. Sir, one doubt, sir.
Hmm.
Sir, it's root 6, so it won't get divided by 2, right, sir?
No, I couldn't get you. What's that? What are you saying?
No, sir. It is root 6, no, sir.
Yeah, root 6, yes.
So it won't get divided by 2, right, sir?
This 2?
Yes, sir.
No, you should not divide this by 2. Because see the option, in all the 4 options, h cross is given. Okay, h by 2 pi is nothing but h cross. So you should not disturb this.
Okay, sir.
Okay, keep this one as such. And you cannot cancel these 2.
Okay, sir.
You cannot cancel these 2. If you want to cancel, you have to bring 1 by 2 inside the square root. Okay, that root you have to follow. But in this question, all options have h cross. Okay, h by 2 pi is nothing but h cross. So you should not disturb this one. That's all. Then question number 50. See question number 50. What is the maximum number of orbitals? Read the question carefully. What is the maximum number of orbitals that can be identified with the following quantum numbers? N equal to 3, L equal to 1, ML equal to 0. Students, observe carefully. Whenever M is 0, it should be an Z orbital, or the orbital should contain Z, pure Z. N value is 3. Okay, observe this carefully, student. If N, L, M are given, then it corresponds to one orbital. It corresponds to one orbital. Very simple. Okay. For one particular orbital, N value, L value, M value is a fixed number for one particular orbital. Okay, you know very well. To designate an orbital, you require 3 quantum number. If 3 quantum number values are given, that means it corresponds to one particular orbital. So the question is, what is the maximum number of orbital they are asking? If N, L, M value are fixed, it corresponds to only one orbital. So correct option is A. If you fix N value, L value, M value, then it corresponds to only one particular orbital. So number of orbital is just 1. Okay, take 2. Clear, student? Clear?
Yes, sir.
Yeah, right. I stop here. We'll continue
sir.
the next class.